Howdy PreCal, it is Miss Kosh. Today we're going to look at transformations first, and then we're going to look at inverse functions. So we're going to kind of do all of that today. I'll probably break it into two videos. Here we go. So a vertical shift is something that's going to shift the graph up or down. And so we have this plus D that shows up here on the outside. A horizontal shift is going to shift us left or right inside. Notice if we have, let's say we're looking at the graph, if I start with f of x equals x squared, I have a parabola. If I say f of x is now, or if I say g of x, we're going to call this g, pretend that's a g. G of x is now x squared plus 2. This has taken our parent function and moved it up 2 units. Okay, if I say h of x is equal to x plus 2 here, this doesn't move it to the right, it actually does the opposite, it moves it to the left 2. So it's going to do, when it's inside here with x, it does the opposite of what you would expect. So outside it does, if it's positive, it's going in a positive direction, but inside, if it's positive, it actually goes in a negative direction. Okay, the next one, we can reflect it over the x-axis by changing the number out front. So if I make a negative, so like if I have y equals negative x squared, that has reflected, and it was here on the outside, that has reflected over the x-axis. So that means when I'm not sure exactly what that blank is for, but that's where a is equal to -1. And a reflection over the y-axis, it depends on what type of graph it is. Sometimes if I had this y is equal to negative x squared, it reflected it over the y-axis, but it already had symmetry over the y-axis, so it doesn't look any different. But this is where the b value, or actually, it could be -1. If all it's doing is reflecting, it's just a is a -1. If it's an a equals -2, then it's stretched and reflected at the same time. Okay, this is where b is equal to -1. Horizontal shifts, vertical shifts and reflections are called rigid transformations because the basic shape of the graph does not change. There's no stretching or pulling or anything like that. It's just, we take a graph and we shift, and we take a graph and we shift, or we take a graph and we reflect, or something like that, but this basic shape doesn't change. Okay, a vertical stretch or compression. Sometimes I'll just use the word dilation, but as a gets bigger and bigger and bigger, it's being stretched farther away. So when a is greater than 1, it's going to stretch. When 0 is less than a is less than 1, when a is between 0 and 1, then it's going to get compressed. It's going to be pushed back down towards the x-axis. It does change. These are non-rigid transformations because it does change the shape of the graph. Okay, but in this one, it's a little bit different. If b is, let's see, basically when, you know what, I just want to use the word dilation. Okay, so if I take, let me show it to you this way. If I'm in my graph, okay, so let's look at the parent function, y equals x squared. Okay, so now if I'm looking at the function and I put it inside here, if I have 2x and I close my parentheses, oh, here's my parentheses, and then I square it. Okay, what this is going to do, here's the parent function and here's the next one. It has compressed it in to the graph. Okay, so it has pushed, I took the parent function that's blue and I pushed it closer to the y-axis, and so I have compressed this graph. And so that was when, so I shrink or compress when b is greater than 1. Okay, I'm going to stretch this now. Notice if I come back here and I say, you know what, I'll type in another one. If I do the fraction 1/2, and then I have my x, close my parentheses, and the whole thing is getting squared. So now I'm going to have a green graph. So there's the parent function, and so from the parent function, the red was compressed and the green was stretched away from the y-axis. Okay, and so this is 0 is less than b is less than 1. Okay, a horizontal shift. So make sure your shifts left and right, you need to have, notice this b is factored out. There's a parentheses here. Okay, then you can see the shift is c. So if I do something like, okay, let's look at my calculator. Let's get rid of this. Delete. Delete. Let's say, actually, I'm going to say this one is 2. So I have now compressed my graph a little bit, but what I want to show you is that if I do 2x plus 4, and then I square that, it's not, notice here, it's not a shift of 4 from that one. We have to factor this out. We would have to write this as 2 times 2 plus 2. I lied to you. That's not an x. Delete. There's my x. Okay, I'm factoring badly, but I'm trying. Okay, does this, if I factor out the 2, here we go. Okay, so now that graph should match, but you can see the shift is 2 to the left in this equation when it's factored out. Okay, hopefully that wasn't too confusing. The first transformation you should do, I would always say, I guess the way I'm going to do it is I'm going to reflect and shift. No, I'm going to reflect and stretch before I shift. So I always start the parent function, reflect and shift. I'm saying the wrong thing. Oh my goodness. The way Ms. Kosh does it, the Kosh style is to do reflections and stretches and then start shifting from there. Okay, so on this one, the parent function is y equals x squared. What happened? Well, we reflected over the x-axis and we shifted, we shifted to the right. 3 units, but we're just going to say right 3. Right. Okay, this one, the parent function is the absolute value of x. We now have a horizontal, am I telling you the right thing? We now have a horizontal compression, but we really need to factor out in this problem. This is the absolute value of 3 times x minus 2. And so now we shifted right. We shift right 2, and this was shift right 3. Okay, on this one, what's our parent function? I see the square root of x. We need to factor out here also. This is 3 times the square root of negative, and then x minus 4 minus 2. Okay, so this has a vertical stretch. It has a reflection over the y-axis, so it's going to change the domain actually. And then we're going to shift right 4, there's a t, and up, no, not up, we're going to go down 2. Okay, the next one, our parent function is y equals x cubed. We have been reflected over the x-axis. We've gone to the left 4 and up 5. On this one, our parent function is the rational function y equals 1 over x. We have gone left 4 and down 3. Cool. Okay, let's see if we can write some equations. Okay, you know what? I have to pull this one up again also because it's too small. Okay. I now have it on my screen where I can read these numbers. Okay, this is 5, 2. This is 6, negative 1, and this is 7, negative 10. So if I were doing this by hand, let me grab a piece of paper. If I were doing this by hand, I would say I have a parabola, f of x is equal, and in vertex form, it's a times x minus h squared plus k. So I can plug in the vertex. This was a 5 and a 2. And now I can plug in another point. I see on here f of 6 is equal to negative 1. So I'm going to plug in negative, so f of 6 equals a times 6 minus 5 squared plus 2, and that's equal to negative 1. 6 minus 5 is 1. 1 squared is 1, so this is a plus 2 is equal to negative 1. Subtract 2, and now I have the equation f of x equals negative 3 times x minus 5 squared plus 2. Okay, this to me is a perfectly good answer, but our calculator is going to give us something different in just a second, and I want to show you how they actually are going to be the same. If I FOIL this, I get x squared minus 10x. So this process you don't have to do. I'm just trying to show you what's going to happen with our calculator. Okay, and this becomes a negative 3x squared plus 30x minus 75 plus 2. And so another way to write this equation is this. Okay, so f of x, I would call this vertex form, and I would call this standard form. different books call different things standard form, but that to me is standard form. Okay, so now what we can do is we can get our calculator to help us here. So if I go to statistics, I can type in these points. I have a 5, 6, and a 7 for my x values, and I have a 2, a -1, and a -10 for my y values, and I can graph that. There they are, okay. And then I can calculate, I can do a regression. I think it's x squared. And so notice what this gave me is they're saying my a is equal to, they're saying my a is equal to -3, so it's -3x squared. My b is 30, and my c is -73. And have we seen that equation before? We sure have. So I had to, my calculator can get me to this differently than I can get there by myself. So the other equation was that y was equal to -3x minus 5 squared plus 2. This makes it This makes it easy to see the transformations. This does not. But this is easy, relatively, in getting it from your calculator. So if those are equivalent, then life is good. Okay, so there was a reflection over the x. There was a vertical stretch. Then there was a shift. We went right 5 and up 2. Okay, this next one, I can't see the numbers. I see a -3, -5. I'm going to write it a little bigger. -3, -5. This over here was -1, -4. And this over here is a -5, -4. Okay, on this one, to be honest with you, we can't really use our calculator. Our calculator, this is an absolute value function, and our calculator won't do an absolute value function regression. So there's that. Okay, so f of x would be equal to, I'm going to say a times the absolute value of x. We shifted, so this becomes a +3 in here, and we shifted down to -5. And if I plug in -1, I should get -4. So f of -1 is equal to a times the absolute value of -1 plus 3 minus 5, and this should be equal to -4. That'll help me solve for that value up front. I see 3 minus 1 is 2, absolute value, so I see 2a minus 5 equals -4. Add 5, I get a +1. So my a value is equal to 1/2. So my function f of x would be equal to 1/2 times the absolute value of x plus 3 minus 5. I have no reflection, I have a vertical compression, and I went to the left 3 and down 5. Okay, oh, this looks like a rational function to me. I hope there's no stretch. That makes life harder. Okay, what do I see? I see an asymptote here. I had to look at the computer screen. I see an asymptote at x equals -1. And I see an asymptote at 1, 2, 3, at y equals, I think this is here at y equals -3. Okay, so if I think in terms of my transformations to write this equation, and once again, I can't do the calculator to do a rational function. It doesn't have a rational regression. F of x would be equal to, let's say, a over, I shifted to the left, so x plus 1, and I shifted down. Okay, so now I see the point 0 is nice to work with. This is the point 0, -5. So f of 0 is going to be equal to a of 0 plus 1 minus 3 is equal to -5. 0 plus 1 is 1. A divided by 1 is just a. Add 3, a is equal to -2. And so my equation, f of x, I needed more space apparently. F of x is equal to -2 over x plus 1 minus 3. Yes, there's my equation. What did it do? It was a reflection over the x-axis. It was a vertical stretch. I'm too lazy. That's an R. I guess I wrote out the whole word. I went left 1, and I went down 3. Okay, that is the graphing part of the notes for today. I'm going to stop here, partly because it's almost time for class. So like, subscribe, comment, and let me know how I can help you. Go practice.